Well, welcome back, folks. Looks like we can get started today. For today's class, we're pretty much just going to get through section 11.9, working on the representations of functions as power series. And it'll be a pretty interesting section because now we're starting to see how all this comes together. We'll be able to differentiate power series, integrate power series, and some of the biggest punchlines to all the stuff we've been doing in chapter 11 so far is at the end of this document. There's more exciting stuff once we finally get to the Taylor series and Maclaurin series, but this is getting us pretty close to that goal. So once we finish off this section, we're going to next, on our Thursday's class, be reviewing for the third exam. And I was mentioning to the class earlier, in our schedule, we're actually a little bit ahead of the schedule, so we pretty much need a review day just to make sure we're not getting too far ahead. So I have the sample exams versions posted here. Summary of tests, this is for the purpose of just studying. You might decide to put information here on your notes or information here on your notes. These are the tests as our authors written them, so the notation's more similar. And these are the same exact tests as a flow chart. So up to you how you want to put down your notes for this upcoming next exam. And if you want even more practice, take a look at this document. Mixed series just has a long line of different kinds of series that you can test for convergence, divergence. None of them are power series, so this is going from section essentially 11.1 up to 11 point, let me double check. Yeah, 11.6. It has solutions down below as well, so you can double check how you're doing as you go to solve each one of them. And these are pretty good solutions. This is a 9-page document showing all the solutions to this one here. Probably the best way to get really good practice on these is just pick a random series, use maybe a random number generator, try to test it for convergence and divergence. And if you're not sure how to start, in a way, that's a good thing. That means there's something to learn on that one. And working on one that looks hard, you're not even sure how to start, is a great preparation for the upcoming exam. Well, let's go back to section 11.9. We'll finish off this one today and then do our review on Thursday. Any questions or comments at all, folks, before we get started? Okay, let's dive in then. Section 11.9. We worked a couple problems already. Here's the second one that we did. So our goal is, we're taking a function, and as the section title says, we want to represent it this way. So as a mathematical function, this has a pretty big domain, all real numbers. But sometimes we prefer to have a power series, and here's that same function as a power series. It gives the same results. It's easier to work with in a certain sense, but the only downside is you have to specifically be in this domain, or else the whole series diverges. So as long as that's the domain of your problem, that function there is just as good as that function way over here. We'll try it out on another problem and then move forward to see how to differentiate and integrate functions of this form, power series. This below is just the major tool that makes it all work. And we'll try it again now next on part C. But did anyone have any questions about any of the work here on this one? Okay, moving on to the next. Here's our part C. Seems to have a lot of stuff going on with it compared to the other ones, but our goal is to first get a 1 here. If we can make that happen, we're on track. We need a 1 right here, and we already have that, so that's nice. So it looks like on this one, there's not actually as much setup as you might think. It's already pretty much in the format we want. We want to get it down to this, following it to the letter. You can factor out 2x power 5. We'll be multiplying 1 over 1 minus 2x squared. Parentheses here are not needed, but it's just to emphasize this part here, 2x squared, plays the role of the x down here in the formula, which means it goes here as a power series. It'll be 2 to the power of n times x to the power of 2n. So now we've got 2x power 5. It's multiplying a summation from 0 to infinity of 2x squared to the nth power. At this stage, we're pretty much done with this as a formula. But let's start simplifying this a little bit more. It turns into, on the next step, a summation from 0 to infinity of 2x power 5, forgot that part in front. We get 2 to the power of n, x to the power of 2n as we distribute the exponent into this factor, or into that product. So now we take the summation as we go from 0 to infinity of 2 to the power n plus 1, x to the power of 2n. We're adding 5 factors of x from the left, so now it's 2n plus 5. So that's our power series. But as a function represented as a power series, the most important thing we need on this is its interval of convergence. That's what this part of the formula is saying. It converges provided the absolute value of x is less than 1. So let's say the same over here. This formula is accurate provided the absolute value, we said of x, but that's the x that goes right in here, which is the x that goes from up here, which means for us, that's what we mean when we say x, the 2x squared in fact. So we take the absolute value, 2x squared, set it less than 1. Now we have to solve this and get an interval out of it, but you can divide out 2 right away. In fact, you can just drop absolute values. This is a positive quantity by the red dot. So we're left with x squared less than 1/2. When we square root both sides, we need to be careful. I mean, in algebra, oftentimes you have things that go like this. X squared is 5, and then we square root it. Say x is plus or minus square root of 5. We're not doing exactly the same thing here because we're dealing with an inequality this time. So instead of using that idea from algebra, we're using this new idea that if you take the square root of a quantity squared, you get the absolute value of that quantity. So square root this on the left, and it's now absolute value of x on this position, less than square root of this becomes 1 over square root of 2. You can leave it like that, or you could rationalize it, up to you. In trigonometry, we'd usually call this root 2 over 2, but I'm totally fine with 1 over root 2. Once we get to here, where it's just absolute value of x less than a quantity, we can make our conclusion. I, the interval of convergence, goes from negative 1 over root 2 up to positive 1 over root 2. So this as a power series represents the original function as long as you stay within this range. If we leave it, then we don't have the same function any longer. Well, any questions at all, folks, at the moment? Okay, so that was our third one that we got to write down as a power series. I guess we could just leave that there as a square, as a screenshot. But we're doing more than just writing things down as a power series. I mean, why would we want to take a perfectly good function with a nice domain, write it in this maddening way, an infinite sum? I mean, that's infinitely many terms, and a reduced domain. There's got to be some benefit to that trade-off. And the benefit is essentially what we said at the very start of this chapter. Let's take another look at it. Section 11.1 says if you can get a power series going, you can actually give a better answer to something like this. This is going to be something we do after Taylor's series, for example. We can't integrate this without resorting to the fundamental theorem of calculus. Sorry, I should be pointing here by the red dot. But if you use power series, we can integrate to e to the x squared. Write it as a power series, which we'll call a Taylor series, or maybe a Maclaurin series. And those ones will have an interval of convergence, all real numbers. They're not as restrictive as what we're seeing right here. So we're starting to get really close to those big punchlines for chapter 11. But before we can get there, all the way there, we need to deal with this big old theorem, differentiation and integration of power series. So it's not as bad as it looks. It just takes a lot of words to describe what you're doing. It makes sense. Power series has infinitely many terms, so there's lots of complexity going on. I felt like for this problem, or for this huge theorem, let's think of it in terms of that. This will be our test power series to look at this theorem under. Okay, so let's call this thing f of x once again, and take a look at the theorem. So it says, assume we have a power series and the radius of convergence is bigger than 0, or potentially infinity. So this is excluding all of those problems where the radius of convergence was 0 and the interval was just a number, for example. You have to have more than one point it converges on, in other words, a total interval. So if you have that, and you have a power series, like this one, much like the one we have down over here, then you can differentiate it. It'll be differentiable on its domain, a minus r, a plus r. This right here, even though it's called its domain, is the interval of convergence. So I is that. How do we know? Well, this is a power series centered at A. It means we already know it converges at A for sure. That's why A is an interval. But the minus r and plus r is because we also had a radius of convergence. So it says, this is the interval. You can go left by a value r, right by a value r, to get your interval of convergence. That's the domain of the function. So now that we have the interval of convergence, we differentiate like this. F prime could be visualized as d by dx, multiplying the power series. But this is actually the huge step. Taking a differential operator and infinitely many terms and switching their order is a huge, huge leap of logic. Our author does not prove this theorem, but if you're taking elementary analysis, real analysis, you'll get close to those kinds of proofs, and your instructor may in fact prove this theorem. It's a wild ride, but once the differentiation operator goes inside, you're taking the derivative as normal. Cn is a constant. It's the coefficient. You're differentiating that then. So that's why you get n minus 1 and n right here. Almost thought I missed that. Don't know why I put it over there to the left, but it's all there. So sure, if you differentiate this just on its own, that would be the result here and here. So differentiation of power series just means we're allowed to take a function like this one and write out this. F prime of x equals summation as we go from 0 to infinity of this part right here is constant, 2n plus 1, so the derivative passes right through it. But what we're differentiating with respect to x is x to the power of 2n plus 5. Already, though, this is a bit of a logical issue if I write it out this way. The index has to start at 1. Notice it's also a 1 right here. Does that make sense, though? Do people see why that should be a 1 and not a 0 when this one started as a 0? I think it's kind of tricky in a way. It's worth investigating. Let's take a look at this a little bit closer. This is our power series, but it's just a huge abstract object, really, right? You can make it more concrete by saying f of x. Our author does this often in the reading. It's equal to, plug in 0 first. You'll get 2 to the power of 1, which is 2. Hang on, let me see here. Plugging in 0 gives us 2 to the power of 1, x to the power of 2n plus 5. Hang on, I think I might have made a mistake in what my first statements were on this one. This one really should start at an index of 0, but this one has to start at an index of 1. Sorry, I made a mistake on this one. Let's write this out anyways to see what that mistake was. We're plugging in 0 first, where it is in the red dot. We get 2, and then x to the power 5. Here's what my mistake was. In this versus this, they're not exactly the same. This is x raised to a high power. This is x raised to the same power n. It goes a little bit differently. Let's keep on writing these out just to explain why that really is a 1 right here. That part is not the typo. So if we plug in 1 next, we'll get plus 2 to the power of 2, so 4, x to the power of 2 plus 5, so power 7. We plug in 2 next. We have 2 cubed for an 8. X to the power of 2 there is going to give us x power 9. And the pattern just keeps on repeating. So essentially all we're doing is differentiating all of these terms at once. We'll make it look like this, but when we differentiate down here, f prime of x becomes 10x power 4 plus 28 x power 6 plus 72 x power 8, and so on. So we're getting infinitely many different terms here. The first term didn't vanish though. That's why this still starts at 0. Differentiating up here, we get f prime of x is a summation from 0 to infinity to the power of n plus 1. Derivative of this x would take the 2n plus 5 portion and make it a coefficient. New power on x is 2n plus 4 altogether. So that's our new power series. And still, there's a weird issue right here on the 1. Let's see how it goes up on this one, just to see how this all comes together. First, any questions, folks, on the expanded series or with the compact one here? Okay, so really the big leap of logic is that right there. We take a derivative as normal, it just looks super abstract because it's being done through an infinite sum all at once. And there's more abstraction going on here because sometimes the index changes and sometimes it doesn't. It depends on the problem. So let's expand out this one as a power series to resolve the issue down here. If we expand out this f of x would be equal to, plug in 0 and we get c0. And now 0 here for the power gives us x minus a to the power 0. It's just a 1. Plug in a 1, we get c1, x minus a to the 1th power, so just x minus a. And down the line, c2, x minus a squared, c3, x minus a cubed, and so on. So if we differentiate this going this way, this is what it would look like. F prime of x equals, derivative here is a constant, so we lose that term completely. It's just gone. We keep this term. It'll be c1. X minus a vanishes in the derivative, so we'll go plus 2c2, x minus a. Do it again from over here, plus 3c3, x minus a squared, and so on. So the reason this index starts at 1 is because when you differentiate this type of power series, the constant term vanishes, and you're indexing starting at 1 instead. So begins there, but this one had a 2n plus 5. That's why the first term didn't go away. If this was x to the power of n, it would have matched that same pattern. Okay, so we can differentiate power series, but notice this statement here. It's kind of a sad statement in a way. It says it has the same radius of convergence, which is r, positive, but it says nothing about the interval convergence, which is unfortunate. It's possible your interval convergence changes. So in other words, if we converged on the left boundary or the right boundary and differentiated, we might not converge any longer on the boundary values. The radius stays the same, but the endpoints of the interval can potentially change. Same if we integrate. Radius stays the same, but we don't know what happens on the boundaries at the endpoints. They have to be tested. But here's how integration goes. Integrate f of x. Well, f of x can be replaced with this thing right here, and the integral sign goes inside the summation, which just means this part right here turns into x minus a to a higher power. We divide by that new power, and this is super easy to miss. It still needs a constant of integration because it is an integration problem. So that's what integration looks like for these things. Let's integrate this function here by the red dot, just for further practice. So if that's our function, and we want to integrate f of x, the process looks like this to start. We're integrating an infinite sum, so infinitely many terms are in the integrand now, to n plus 1. Whoa, my pen seems to be upset. X to the power of 2n plus 5 dx. So all we've done in this first step is just substituted in the power series into that integrand. You don't have to show this step, but it's not a bad one the first few times you do it. Let's commute the integral sign here through the summation symbol. This is the step that made people really, really uncomfortable in the past, and it took a lot of hard mathematics to say what the conditions were to allow this to actually work. So summation from 0 to infinity, 2 to the power of n plus 1, it's constant, so the integral lands right here on x to the power 2n plus 5 dx. So it's an optional step, but I think it's a helpful one because these problems are tricky enough. This is just to help us visualize what's going on. So last step, we have to add a constant of integration c. It looks kind of funny. It's put in first, but in calculus, we usually put it in last if it's not a power series. The reason we're putting it over here is if we put it over here like that, it's easy to get a misconstruing that the summation also involves c here. But no, c is only added once, not infinitely many times. I don't care too much where you put your c as long as it's clear that's not being part of this sum. You're just fine. So we're integrating, we have a constant c. We'll throw in plus summation from 0 to infinity. Copy in the constant 2n plus 1. Excuse me, 2 to the power of n plus 1 is the right way to say that. And this is just an ordinary integral from calculus 1. The new power of x is 1 higher. So it's x to the power 2n plus 6. So we divide by that new power, 2n plus 6. So here to here, that's the result of integrating the power series. This one does index at 0. Because if you integrate the first term, it doesn't go away. You just increase the degree of the value of x. Yeah.
So above where it went one, was that just kind of like stylistic stating that the first term disappears, or was it needed to be stated that way?
It was needed in this one, yeah. You could re-index the sum and say now it's re-indexed back to 0, going to infinity. But if you did that, you have to go, let's see, it went down by 1. Everywhere there's an n, you'd have to put in n plus 1, c n plus 1, x minus a to the power of n. So if you index that in 0, you'd have to write in your answer that way. So yeah, it's kind of weird. The only reason it doesn't start off at 0 is because there is no c0 term whatsoever. There's only a c1 term. Does that make sense with that question there? Okay. Other questions at the moment? So the punchline is, this is a pretty weird power series, but you can differentiate it. It differentiates as normal. And integrating a power series as well, it looks really weird, but just do exactly what you did in calculus 1 and you're in great shape. That would be the antiderivative there. So with our test power series here, here's the 2 results. This was an anomaly because the power of this was not power n. So we started still at index 0. So what we're going to be doing next is more of the same kind of things that we started off with. Example 1 of this on these notes were find a power series representation of this function. It was just ready to go though. We didn't have to do anything special to get started. But here's now the tricky ones. In our new problems down here on example 1, we try to use this old formula that we use. This is example 1. Sorry, that should have said example 2. Counting must have been hard that day. Put that in red dotted. I mean, it's an honest edit. So let's say 2 for example 2. This is the only trick we had back when we were dealing with example 1. And it doesn't work here. You can't match up a natural log with this kind of stuff. Which means we have to do something else to this function. And pretty much it's all up to us. We have to do something to that some way, somehow. Any suggestions from the class? Here or over Zoom?
Take the derivative.
Absolutely, good call, Steve. It's almost what we want, right? It has a 1 plus something. That's down here. We could correct it and make it a negative, but it's trapped in a natural logarithm. So we're sort of stuck until we differentiate. Like you said, differentiating takes this entire input and throws it into the denominator. So that's our first step. Let's write this in blue. F prime of x is 1 plus x squared. By the chain rule, we multiply by that and get a 2x in the numerator. Now, suddenly this formula is back on the table. We can work this now. So same as example 1, let's factor out the 2x. It's going to multiply 1 over 1 minus negative x squared. This part that's in the parentheses is what we throw into the power series. So now we have 2x with a summation from 0 to infinity of negative x squared. Excuse me, not squared, that way. Negative x squared that way, and then all raised to the nth power. Must have done a micro sleep right there, but the record's corrected on that one. So that's what our new power series looks like. It says on the instructions, find a power series representation and determine. We just want radius of convergence this time, because the interval convergences change upon differentiation and integrating. We're not going to investigate it too hard. We'll settle for the radius. Let's also simplify this as much as feasibly possible. It'll be helpful on the next steps. It's now 2x, sum from 0 to infinity, negative 1 to the nth power, x to the power of 2n. We can distribute the x inside that and get 2 times the summation from 0 to infinity, negative 1 to the nth power, x to the power 2n plus 1. So we now have a power series, but here's the trouble. It's a power series for f prime of x. We still want an f power series for f of x, so we'll get across that logical issue. But first, let's work on the radius of convergence. So this equality right here by the red dot is only valid provided the absolute value of something is less than 1. And that something is this over here by the red dot, or you could be looking over here, the thing that you threw into the power series. So we need negative x squared to be less than 1 in absolute value. Already, this implies that the radius of convergence is 1. No harm if you did extra algebra, you would say x squared less than 1, handling the absolute value symbol. Square rooting both sides gives you absolute value less than 1. And so we have radius 1 in this problem. But that's a radius convergence for f prime. However, the good news is if we differentiate this as a power series or integrate it as a power series, the theorem above told us radius of convergence never changes. It's the interval that might change, but not the radius. Okay, these problems are a little bit long, and it's kind of easy to lose your way on this kind of stuff. Because once again, we're going for a power series on f of x, not f prime of x. But actually, this is a weird little issue that we looked at on the very first day of class. On the very first day of class, we mentioned f of x is equal to the antiderivative of f prime of x dx. So that's a nice little formula, essentially saying if you have a derivative here, but you want an antiderivative of the derivative, you're talking about the original function. That helps us up massively, and it brings the last theorem onto the table now, because f prime of x, we have written in as a power series. So here's our next step. F of x, which is natural log x squared plus 1, let's say that right now, just to be specific. is now 2 times the indefinite integral of summation from 0 to infinity, -1 to the nth power, x to the power 2n plus 1 dx. So once we resolve what all this is, we have a power series representation of natural logarithm x squared plus 1. So that's the trick on these new batch of problems. This formula is really restrictive, but on some settings, if you differentiate the right thing, it comes back into play. This doesn't always work either. That's why we go to section 11.10 and get an even bigger method called Taylor series, Maclaurin series, for when these kind of tricks fail us as well. Let's continue on and just integrate the rest of this. Natural log x squared plus 1 is now 2. Just taking a little bit extra time to visualize what's happening. It's 2 times the summation from 0 to infinity, -1 to the nth power, and we're integrating x to the power 2n plus 1 dx. So again, the major issue with that theorem we were looking at above is that the integral sign does in fact commute through summation for these power series. So now we're just going to take that antiderivative and mostly be on our way. There's still a few more steps we have to resolve. Any questions at all, folks, to this stage though? Okay, let's finish it off. So we have next natural log x squared plus 1 equals a constant c. We're putting in the constant because we're finalizing our last integration. 2 times the summation from 0 to infinity, -1 to the nth power. New exponent on x is 1 higher, so x is now to the power 2n plus 2. We divide by that new exponent, 2n plus 2. And we're almost there, folks. We have a power series representation of natural log x squared plus 1, but it actually isn't totally complete. This is kind of surprising, but in this context, we must solve for the integration constant c. The reason for that is if we're looking for a representation of natural log x squared plus 1, we can't have infinitely many answers, and that's what c is representing. It's any real number whatsoever. We want the one real number that represents all of this as a power series for natural log x squared plus 1. So we have to solve for that constant c. The trick to that is we need to find the center of this power series. That's really our best hope. So that's yet another interesting question. So good question for the class is the center is x equals, anyone spot what the center of this is as a power series? Absolutely. If it's just x raised to a power, center is 0 on these ones. The only way it's not 0 is if you had something like, let's take a look at another one real quick. So something like maybe, I forget, these take a moment to load. This one is centered at 4/5. I keep on saying 5/4. It's centered at 4/5 because that's the value you can put in for x to get a 0 right in that location. So that's why it's the center of that one. This one has a center of 0 because the one value you can put into this location to wipe out the entire power series. So we want to take, in our problem, let me get these pens realigned. Natural log of the center should go in on the left. 0 squared plus 1 equals the constant c we're solving for plus 2 times 0. We just killed this power series completely because if we're plugging in x equals 0 right here, every single term is 0 altogether. Yeah. Gotcha. So one thing that also is kind of common in these problems is constant of integration is often zero. It doesn't have to be, but I think you have to work kind of hard to make it a non-standard question. So you should have work that comes out about like this. On the left, it's natural log 1. On the right, it's the constant c of integration, but natural logarithm of 1 is 0. So we found 0 equals c in this problem. That means we are actually really done. We just need to say our answer. Let's use the triangle. We did a lot of work, and now we're saying, by all this work above, we have, therefore, natural log of x squared plus 1, now as a power series, is a summation as you go from 2 times that summation, rather, as you go from 0 to infinity, negative 1 to the nth power, x to the power 2n plus 2, over 2n plus 2. I really didn't do anything too much new from way up here, except we deleted the constant c. We found it had to be 0 itself. But we did, folks. This is just like example 1, but we're starting to get more and more functions, like natural log x squared plus 1, that we can represent as power series in this kind of way. Any questions on how these steps went together? Okay, also notice no crazy trickiness with the index starting at 0. When you integrate, it still starts at 0. There is an additional term, but that term often goes away as a 0 as well. So let's try it out again just for the sake of extra practice. Here's the next version of those same kind of problems. We want a power series representation of this thing. We also want its radius of convergence. Oh, that means I did forget something on this problem. We did say it, the radius of convergence is 1, but we should re-say it at the very bottom, because this was a conclusion for f prime of x. Down here, we want to say, just as a reminder, r equals 1. So the note on this is, it has the same radius of convergence. All right, con for short for convergence on that one. So let's try this out all over again. This time we have a product, x squared tangent inverse of x cubed. And like before, we might try differentiation to make that work, because we do know, for example, that tangent inverse of x prime is a 1 over 1 plus x squared. That's helpful because that means if we differentiate tangent inverse x, or even this thing right here, we should be able to use the same exact trick, that formula, where'd it go? I lost my formula. With that same exact trick with the power geometric series to represent this function. But notice what's kind of surprising about this problem is you don't want to duplicate the same exact thing. If you differentiate the whole function, now you're using the product rule, you're making the problem a lot bigger. You might have 2 power series you're dealing with. It's of no help at all. So on this problem, what you want to do is start splitting things apart. Let's focus on just that part right there and get a power series representation for only that one piece. The one piece we know we can differentiate and use the geometric series on. So we start by saying, let some new totally new function g of x be equal to tangent inverse of x cubed. Starting off the same exact way like Steve suggested, we can differentiate it. We get g prime of x is equal to 1 over 1 plus x cubed squared, and then we multiply by the derivative of x cubed through the chain rule. So first step is, after differentiating, 3x squared up above, we have a 1 plus x power 6 down below. So we're getting back to that original format. I seem to have deleted that screenshot. I don't know where that went. But let's just write out again. 1 over 1 minus x will be summation from 0 to infinity. of x power n. So that's pretty much how our formula is written out. Continuing forward on this one, if it's helpful, we can clear out the denominator. Doing that is just to force this part to match up. We have the 1 now. We have the 1 we needed below. So let's insert it 2 double negations. And now we've matched up that part of the process. So we're in business, folks. We can now say that this is a summation. Well, it's easy to forget this part. Don't forget the 3x squared times the summation from 0 to infinity of negative x power 6 raised to the nth power. And I think I'm trying too hard to squeeze that in. Let me write it out better. Turns into 3x squared summation from 0 to infinity of negative x to the 6th power raised now to the nth power. So that's the use of this formula below. Any questions at all, folks? Getting going with G prime as a power series? Okay, power series representation of the whole function is really, really tough if we try to treat it as one entire complete function. So we get a toe in by just breaking off one piece that we can work with. Now we have a power series. We can start involving the whole function. But same problem as before on part A. We still don't know the power series of G prime, or excuse me, of G of X. We have it for G prime. So we need to simplify this as much as possible so we can next integrate it and get G of X itself. So continuing on in the simplification, we have 3 times x squared. Sorry, I'm struggling with this penmanship here. Let me write it out better. 3x squared this way. Sum is from 0 to infinity. Over here, we break up the product, make negative 1 to power of n, multiply x to the power of 6n. And finally, this is the major step that gets us in a good spot for integration differentiation. We'll leave the 3 there. There's no base to throw it into. But that's okay because it's a constant. Integration that's not going to be affected much by it. Negative 1 to the nth power. And x to the power of 6n gets increased by plus 2 coming from the x squared. And so there it is in its most simplified form, ready for integration in our next step. All we really want to say now is what the radius of convergence is going to be. We do it the same way. We go right here where the red dot is and say, all of this works provided the absolute value of negative x to the 6th power is less than 1. And just like before, this implies x to the 6th power is less than 1. You could start taking square roots on this thing if you like, but the more you work with this, the more you're going to realize this all just implies right away, from this alone, radius of convergence is 1. But I really did skip a couple steps to get to that conclusion. Let's leave it up to the class. Should we continue to work with this inequality just to show logically step by step how we end up there? Looks like some people are okay with it. How about for folks in Zoom? Is this okay with that shortcut there? Doesn't look like anyone's too opposed. Kind of the thought about it is, if you go to just take the 6th root of both sides of this, it will be the absolute value of x on the left-hand side. And the 6th root of 1 is just 1. So in this kind of configuration, really from here alone, you can tell the radius of the convergence is 1. So that means in our end answer, we just have to state radius of convergence for this thing up top as a power series, also 1. So now that we've done that, we still don't have the function in blue. That's g of x, but we can say g of x. We're copying what we did in part A. It's the antiderivative of g prime of x, which means instead of writing out all those steps like we did before, if you want to take a shortcut here, here's what it would look like. go right to this spot by the red dot. Write in the power series summation from 0 to infinity. -1 power of n. And then finally right here, integrate x to the power of 6n plus 2 dx. And if you just wrote in what the antiderivative of that is, that's an okay step to skip as well. We don't want to skip too many steps or else the notes is unreadable. But I think this is a good paper trail so far. We replace g prime of x, and because we're integrating the only thing that's not constant with respect to x. That was x to the power 6n plus 2. So almost there, we get 3 times the summation from 0 to infinity. -1 to the nth power. X is to the power of 6n plus 3 now. So we divide by 6n plus 3. Oh, good call on that one. I should have put that in right up here in the front. I think I just forgot on that one. So it should have been the constant c, like you said, plus 3 times that. Thanks for spotting that one. Highlighting there just to show that omission. Now, that's important because what it implies is we have infinitely many different answers that are potentially correct, but there's exactly only one answer that actually is correct. We're going to solve for it and just see what we get. So we need to remind ourselves, what is g of x in the first place? It's tangent inverse of x power -3. Let's say that all this work implies tangent inverse x power 3 is now equal to that constant c plus 3 times the summation from 0 to infinity, -1 to n, x to the power 6n plus 3, divide by 6n plus 3. That's a lot of copying, but we're just about there. Next thing we want is the center. This one is also centered at 0. Which is important because that means to solve for the constant c, really the only thing that we can do is plug 0 in for x. Left-hand side is now tangent inverse of 0. Right-hand side is the constant c plus 3 times. And let me fix this color coding here. I want to just emphasize we put in 0 for the center. Sure, it's 0 cubed, but still 0. Throw in 0 here as well. And this is what it turns into. So now we're dealing with a tangent inverse 0, but it just so happens that because tangent 0 is 0, tangent inverse of 0 is also 0, and 0 equals c on this problem. Like we mentioned, that's pretty common. I think this is pretty much what happens on the homework, but it's good to know how to go through these steps right here because there's no guarantee. C could be pi over 2 randomly, depending on just a small tweak in the problem. Well, now that we've got that, we're starting to put things together, but let's go up to the top where our original function is. Scroll down just a little bit. And here's our next step. We wanted a power series representation of f of x, but now we know through all this work right here, tangent inverse of x cubed is 3 times sum from 0 to infinity, -1 to the nth power, x to the 6n plus 3 power, 6n plus 3. It's kind of impressive how much copying that is. And that's what's going to go right here. So we now can say f of x equals x squared tangent inverse of x cubed. Just want to write that in so we can lose the screenshot. It's now equal to x squared multiplying the power series representation of tangent inverse of x cubed, all of that stuff. So times 3, summing from 0 to infinity, -1 to the n, x to the power 6n plus 3, 6n plus 3 down below, And here's our final step. All of this is now equal to 3 times the summation from 0 to infinity, -1 to the nth power. And the last step I'm doing is we're multiplying this by x squared, so that becomes a 6n plus 5. X to the power 6n plus 5, divide by 6n plus 3. We're almost there. We just have to state the radius of convergence on this thing. But think about how dangerous this problem is. Instructions say by the power series representation. There it is. The instructions then also say find the radius of convergence. And if you heard that, you might think, oh, we need to hit it by the ratio test. And you could do that. You could use the ratio test here. But what that theorem is telling you is radius of convergence doesn't change. You can totally skip the ratio test and just restate it right here. So integration, differentiation, or just recombining these things together never changes our radius. So we did it, folks. This is a really weird function, but if we need it in a different form as a power series, that's what it turns into. Well, any questions whatsoever, folks? Getting through that slightly nastier one? Okay, well, we're just about done with all these problems. We have 2 more problems left over for today to take a look at. And like we mentioned, this is the good stuff. This is kind of the reward for having power series. We can actually solve these integrals in different ways now. Full disclosure though, this integral you could solve using chapter 7 techniques. You have to factor this as much as possible, use partial fraction decomposition on that, then integrate all those terms. It's very doable. I would say it's like a 40-minute problem. Longer if you make mistakes. It's a pretty long answer on that one, but you could do it. The benefit for us now is if we just want to evaluate the indefinite integrals of power series, far, far less steps for us to work out. Here's how it's going to go. In step 1, we're going to take everything we see here and just rewrite this as a power series. We're using up those same steps as before. So we'll have x, 1 minus x power 8, turns into x times 1 over 1 minus x to the power of 8. Parentheses here just to say that's what's slotting into the power series on our next step. So on the next step, it's x times the summation from 0 to infinity. We take this, raise it to the nth power. So now it's x to the power 8n altogether. Then we need to simplify it as much as possible. So we distribute, or we factor x back into this, multiply it back in. It's a summation from 0 to infinity. X to the power of 8n plus 1. And you know what, I take it back. It is right to say x is distributing into this group, because remember, this is like a parenthesis containing infinitely many terms. You're distributing it back in legitimately. So that's what this all turns into. And this works provided the absolute value of x to the 8th power is less than 1. We can take the 8th root of both sides and just be left with the absolute value of x on the left. 8th root of 1 is just 1. So like we mentioned on the last one, this is a pretty standard shortcut. This implies immediately radius of convergence is 1. So now we have this stuff. We can slot it into the original integral and solve it that way. So we have the integral of x, 1 minus x to the 8th power dx, is now the integral of a summation from 0 to infinity, x to the power of 8n plus 1 dx. So now we're just integrating this. Again, this is a lot less steps, so that's kind of nice in a way. Let me put in the first thing that is most likely I would forget in this problem. Because this is just a full-on find the antiderivative, you need a constant of integration c. And confusingly, this time we are not solving for c. It's much like these problems where you're, say, doing antiderivative of x, you would say a half x squared plus the constant c, but we don't solve for it. Only reasons we were solving for constants on the above set of notes is because we had a definite function that we were working with. We want to know what tangent inverse is, not tangent inverse as it differs by a constant. So in these problems, the constant just stays there. Then here's the last step. Integrating all of this is going to give us a new summation. Still starts at an index of 0, goes up to infinity. Inside the summation, we're taking an antiderivative. So the power on x is 1 higher, 8n plus 2 now. Denominator is 8n plus 2. And that means we took something that is impressively hard as an antiderivative, and it didn't actually take too much paper to get right to here. That's our answer, and it has r equals 1 for its radius of convergence. We don't even need the ratio test on this thing because our powerful theorem above we were looking at guarantees the radius stays the same again. Well, we did, folks. That's a pretty tough antiderivative. Any questions on solving that one? Okay. As an antiderivative, we have to be honest, though. The domain of this thing as an antiderivative is restrictive. It has a center of 0. You can't go too far to the right or the left because the radius is 1. So aside from that one technical issue, this is a fast process. Let's try this out again. X cubed natural log 1 plus x. Oh, weird. That must have been just a micro sleep on my part. Should have been an 8n plus 2, matching the new exponent. Thanks for spotting that one. Let me highlight it just to indicate that weird omission or typo mistake. Does that make sense there with the correction? Awesome. So let's try this out one more time. X cubed natural log 1 plus x. Same kind of thing as before, but I guess any questions first before we try this out again? Okay, what makes this one a little bit different, it's kind of like this part B on the last example, is the fact that we have to deal with that separately. We don't want to necessarily find the power series representation of the whole thing all at once. So we begin by saying, let g of x be equal to the natural log of 1 plus x. We want a power series representation of that thing, but we can't get it just yet. We need to differentiate. So we'll say then g prime of x is 1 over 1 plus x. Chain rule is not impressive here. The derivative of 1 plus x is 1, so we did it. The chain rule is done. This is not totally in the right format. We need minus right by the red dot. So let's change this algebraically to 1 over 1 minus negative x. So that portion right there goes inside the power series as summation from 0 to infinity, negative x power n. And it's kind of nice this time. There's not a bunch of stuff in front. It's a little bit more simplified, but we still probably want to simplify it even further. Always a good call. So take summation from 0 to infinity. This breaks down as negative 1 to the nth power, x to the nth power. So we've got our g of x done. G of x is natural log of 1 plus x. Or excuse me, we have g prime of x done. G prime of x is all of this. Now to get it back to the natural log of 1 plus x, here's our next step. We say g of x is the antiderivative of g prime at x dx. And so now when we go to write this out, we're dealing with the antiderivative of a summation from 0 to infinity, negative 1 to the nth power, x to the nth power, dx. So all that happens in this step is we took our hard work from above through the power series down inside here. So finally, one more step. We have a summation from 0 to infinity. Oh, let me control Z just a little bit first. Don't forget we're solving an antiderivative, so we still need a constant of integration C. Plus now, summation from 0 to infinity, -1 to the nth power, x to the power of n plus 1, since we're finding its antiderivative, divide by n plus 1. So we integrated that portion of the power series. Now that we got here, the next thing we have to do is resolve what is the constant C. Unlike this problem above, we're integrating a function. We leave the constant C here, so we have infinitely different answers. But here, we're trying to resolve what is this g of x. We have to define it definitely. So we need to know what C is. But it's the same exact trick as before. We look at the center of this thing. This is centered at x equals 0. A great way to think about the center is that it's the number you plug in right here to kill off the power series entirely. Everything is wiped out when x is 0. But we also have to plug the center of x equals 0 all the way here on the left, g of 0 now. So we'll have g of 0 is equal to, then finally, all the way here on the right, it's going to be constant C plus 0, because we plugged 0 into that location. Everything is now killed off. So from this step right here, we can say g of 0, this almost feels like deja vu, by the way, becomes natural log 1 plus 0 equals a constant. So now we have natural log 1 is that constant. The natural log 1 is 0. This is the deja vu part. And so that means this constant is just gone. Just to rewrite it, g of x is equal to summation from 0 to infinity, -1 to the nth power, x to the power of n plus 1, divide by n plus 1. So now we know this part. We have a g of x, in other words. And downside to this is, I did forget one thing. We want to integrate this and write the answer as a power series and then state its radius of convergence, which means the easiest time to state the radius of convergence is not when you get your answer. In other words, you don't want to use the ratio test on this if you don't have to. The easiest time to state the radius of convergence is right here. This formula worked provided the absolute value of -x is less than 1. And that's enough information for us already to say radius of convergence is 1. Really don't have to do any further algebra to establish that. So saying that one thing right here and now means we don't need the ratio test to finish off the problem. We can now just say, coming back over here, antiderivative of x cubed times natural log 1 plus x dx turns into this. Recall natural log of 1 plus x, we named it as g of x temporarily, and now it's all of that, a big mess. So it turns into antiderivative of summation from 0 to infinity, -1 to the nth power, x to the power of n plus 4. The n plus 4 came from the power 3, combining with this power 1 right here. When we multiply x cubed against this power series, it just goes up to the 4th power. It's still divided by n plus 1 dx. So the moment we integrate this whole thing, our work is done. We obtain a new constant of integration C, but this constant comes from doing an antiderivative, an honest one. So that's the constant we don't solve. We add to it a summation from 0 to infinity. It's -1 to the nth power. Integrating means power goes up by 1. So n plus 5. Down below, we have n plus one multiplying n plus five. And so finally, we've got an answer, folks. As a power series with kind of a meager radius of convergence, r is 1, that's the antiderivative of x cubed natural log 1 plus x. And something fun to do on this problem is, let's go to a calculator. Wolfram alpha. Because this is not a very nice integral, unlike the first one, which is just a power series or a partial fraction decomposition problem. If you say integrate x cubed natural log 1 plus x, Wolfram might struggle with this one. Let's see what it comes up with. It's, you know what? They found an answer. It's a 48th of 12x41, and it's a whole bunch of different stuff plus a constant. I really don't know how they would have done that. There's some way somehow to get that to happen. Probably massively creative U substitutions and other techniques got to there. But for us, it was a long problem. But once we got through the power series representation, the integration is immediate. So that's kind of the good news. When we do this again as Taylor series, Maclaurin series, the radius of convergence is going to be a lot bigger. For plenty of the problems, it's actually infinity. But we did it, folks. This is getting towards the end of chapter 11, finally. Any last questions or comments before we call it a night? Okay, with where we're at in the schedule, we are legitimately exactly one day ahead now, if you check the syllabus. That means tomorrow pretty much has to be a review day. So come armed with questions you'd like to discuss for a review, and we'll take on as many problems as we can in our 67 minutes of time. But have a great night, folks. Drive safe, and we'll see you all tomorrow. For the final, yes, I have 2 built-in days for that one. Yep, have a good one. You bet.